When cameras are used in a machine vision system, they need to communicate the acquired pixel data with a host computer for doing the image processing. The host computer is computing algorithm for image analysis, and it means that we have a communication channel between the camera and the host computer. And today we are going to discuss about different available protocols and interfaces available for video streaming, communication of pixel data from the camera to the host computer, as well as also different methods for synchronization of the image capture and exposure in the camera with the image processing in the host computer. So the outline of the talk today will be what's inside the camera, and we will refer to the camera interface and how it relates to the other parts of a camera. We will discuss different kinds of camera interfaces, the old-fashioned analog interface, as well as also a number of digital video signal interfaces. And we will discuss different kinds of acquisition modes and synchronization of camera and host computer. So we start with what's inside the camera, and you know, we have a lens that is focusing the light that is reflected from the objects of interest, and the image is then focused through the lens onto the surface, the photosensitive surface on the image detector. And the image detector is then driven by a sensor driving hardware that controls the programming registers and communicates with the image detector. And this hardware is synchronizing and sending pixel data further to a communication interface. And this interface is then used to send a stream of video to a host computer. But today we will focus our discussion on the camera connection and these interfaces. I will start this discussion about video interfaces with the old-fashioned analog video signal. A video signal that was used for broadcasting of TV back in the old days. And the camera and the display system were based on CRT, cathode ray tubes. On the camera side, the cathode ray tube was used such that an electron ray was scanning over a photosensitive area, and depending on the current of this electron ray, it was possible to measure the intensity of light on this photosensitive area. And an interlaced scan mode was used, which means that lines are progressed interlaced with the odd field first, and then after this comes the even field. So all the odd lines were sensed firstly like this until the end of the last odd line, and then there will be a transfer at the end of the photosensitive area until the beginning of the photosensitive area. And during all of these transfers there is a blanking, which means that you are cutting off the video signal during this time, and there is just the black level on the video signal. And after the odd field, the camera is continuing to sense and sending all the even lines until it reaches the end of the sensitive area and starts again with the odd field. At every transfer from the end of a line until the beginning of the next line, there is a horizontal synchronization, and at every transfer at the end of an odd field or an even field up to the beginning of the photosensitive area, there is a vertical synchronization. And both the analog video signal and the synchronization information is merged into a blended something called a composite video signal. That's why we also have a definition for different threshold levels. So the blanking, which means that if you have an analog signal that is lower than this threshold level, it means that the video display should be dark. We have a blanking at 0% of the dynamic range. And we have minus 40% for the synchronization level. So it means that if we have a video signal that is lower than minus 40%, then we have a blanking signal. And above the black level, which is the 0 level of the analog video signal, that is the span that is used for transfer of the actual analog video signal. For the American NTSC standard, there was a field speed of 60 fields per second and a corresponding then image speed of 30 images per second. The higher field speed was a technique used to avoid flickering that can be observed by the human vision, because of if too low update frequencies used, then the human vision will perceive a flicker on the display. So this analog technique is something that we have inherited from the old TV system and the old CRT display and cameras. The use of a digital video stream, on the other hand, means that the analog video signal needs to be converted, needs to be sampled and digitized by the use of an analog to digital converter. And the output data from this analog to digital converter is then used as a stream of pixels. And at the same time, we need, in a similar way as for the analog video signal, we need synchronization information to be combined with this digital video stream. Normally for digital video streams, the synchronization signals are made explicitly. Like in this diagram, you see a pixel clock, and the flanks of each one of the pixel clock means that those are the times when a digital word of pixel on the data bus is transferred. The frame valid signal is activated during the time period whenever there is a complete video frame, an image that is transferred on the stream of images. And the line valid means that this one is active whenever there is a individual line on the image data that is transferred. And you can have the pixel data transferred as one or possibly more pixels per clock cycle, so you can add more or less of pixel parallelism in this video transfer. And I would say that this is a typical arrangement of a video stream that comes out of many of the available CMOS imaging detectors, like the ones from Aptina, Melexis, Kodak, ON Semiconductor, and so on. But also then other protocols for the detector readout, they exist, and there is no really a standard for the video streams on the detector level. Camera Link, on the other hand, is a standard that is maintained by the Automated Imaging Association, AIA, and you have a link for their webpage available here. This standard is further built on something that is called a channel link, and this is an interface that was originally developed and supported by a chipset from National Instruments. And this chipset is using a number of twisted pairs of LVDS, low voltage differential signaling. It's low voltage digital interface capable of transferring 1 bit of data using a pair of wires that are transferred, and there is a matching of the impedance on the sender side and on the receiver side to avoid reflections and provide a reliable transfer also on large distances, also providing a large amount of noise immunity. And you see here that you have a transmitter chipset and you have a receiver chipset. The parallel data input, 28 bits, are divided onto 4 channels. Each one of these channels are transferring 7 bits of data at each flank of the input transmit clock cycle. And you can then understand that you need to increase the speed of the transmitting clock frequency using a phase lock loop and an internal clock generator, such that for each one of the clock cycle of the transmit clock there are 7 bits of data transferred on each one of these pairs of a LVDS channel. The last 5th channel is used for simply transferring the transmit clock to the receiving chipset where you have the receive clock. And altogether this chipset will then provide a bandwidth of a total of 2.38 gigabits per second using a clock frequency of 85 megahertz on the transmit and receive clock. Camera link is a standard for transfer of video streams that are commonly used in industry for machine vision systems, for automation of production and so on. And as I said before, the camera link interface is built upon a number of channel link modules. And if you look at this diagram here, you see that the camera link appears in 3 different configurations: the base configuration, the medium and the full configuration, depending on the requirements of the bandwidth to transfer. And for the base configuration there is only 1 cable, but if you are using the medium and full configuration you need actually 2 cables to connect a camera to a frame grabber that is residing inside or close to a host computer. The base configuration, there is a number of low voltage LVDS channels that are used for control of the camera, control signals from the frame grabber, as well as also serial communication to and from the camera and in between to the image grabber. There is a channel link chipset, transmitter chipset, as I showed you before, that are transmitting using a clock frequency of 85 megahertz, transmitting 24 bits of pixel data together with the control signals, synchronization, line valid, frame valid and data valid. And then it can be combined, as I said before, with an additional data link module and another data link transmitter to make a medium configuration. And for the full configuration you have 3 channel links, but for the last channel link there is only 16 bits of pixel data used, and altogether we will end up in total of 64 bits that are transferred each clock cycle at a speed of 85 megahertz. There is available a total of 72 data bits, but only 64 are used. There are reserved data bits for future extension of the standard. And as I said, the camera link at full configuration provides 64 data bits at 85 megahertz clock cycle, and this will end up at a bandwidth of total 5.44 gigabits per second. And this camera link standard is common in industry for machine vision applications and automation. Some other possible standards are the IEEE Firewire that you can find sometimes on computers, on laptop computers for instance. Provides 1600 megabits per second, and the USB 2.0 is very common, of course, a serial interface providing 480 megabits per second. USB 3 serial interface comes in 3 modes, for backwards compatibility, and the super speed, the highest speed for USB 3.0 is 4.8 gigabits per second, and high speed 480, that is compatible with USB 2, and full speed of 12 megabits per second compatible with USB 1.1. And there is a standardization for USB 3 Vision that is compatible with the USB 2.0 configuration. It is the high speed configuration. Provides 350 megabits per second. Gig eVision, that is a standard that is based on Ethernet communication, provides 125 megabits per second, and Ethernet is a serial interface for usually used for these local area networks, and these LAN, local area networks, comes also in different configuration: 100 megabits per second, 1 gigabits per second, and 10 gigabits per second. I'm now going to discuss with you about different mechanisms in order to make the exposure in the camera, the communication of the image data output from the camera, as well as receiving the pixel data at the frame grabber, transferring from the frame grabber into the memory of the computer, and also starting this image analysis process in the computer. All of these processes needs to happen in a synchronized way, and we call it different kinds of acquisition modes. We can start to have a look at this diagram that I have developed, and you see a sequence of images that are exposed here on the top line, showing what is happening in the camera. So we have the exposures and we have the readout, the communication output of pixels, and we can conclude that this camera has an interleaved capability of doing the exposure and the readout of previous image at the same time in parallel. On the computer side, we have the grabbing process that happens for the corresponding images, as well as also that we are starting the image processing at these time points. And what we can conclude here is that the communication output, the readout and the grabbing of the pixel data are of course happening at the same time for the same image. That is kind of fundamental. And then there is assumed that there is a DMA, direct memory access transfer, from the grabber hardware into the internal memory of the computer that is used for image processing. And then the image processing task, in this case for synchronous image acquisition from a free running camera, as we call it, needs to wait for the grabbing process to finish before it can start. And since we have this lack of capability to do the image processing in parallel with the grabbing, it means that the processing speed in this case will be less than or equal to half of the frame speed. We can continue on the next slide. We call it asynchronous image acquisition from a free running camera. And the difference here, from the previous presentation slide, is that in this case the DMA transfer from the grabber hardware to the internal memory of the computer and the actual image processing itself can happen in parallel at the same time. So we are processing the by use of image analysis at the same time the previous frame, at the same time as we are grabbing the current frame. And in this case we have a processing speed of less than or equal to the frame speed. And we can continue on the next slide, where we have this triggered asynchronous image acquisition from an asynchronous reset camera. This is a snapshot, and this means that there is a triggering event that will start the exposure. So the exposure in the camera will only happen when there is something happening, an event. It could be like a photo cell that is detecting that some object is coming and passing by on a conveyor belt, so we need to make an image and process the image. But anyway, we have a trigger input that comes into the camera that starts the exposure at repeatedly times. Then it means that no longer can we have an interleaved communication with the exposure, but we have a sequential happening on the exposure. So after that we have done the exposure, then we will start the communication for this triggered event. The grabbing in the grabber hardware and the transfer to the internal memory will happen at the same time as the communication output on the camera, and then there will be a start of the image processing after that the grabbing has finalized the transfer of image data into the internal memory of the computer. So the processing speed is, in this case, is like less than or equal to the frame speed. So as a summary from this lecture, I can say that we have discussed different ways and protocols for communication of video stream output from a camera, and we have been discussing also how to take care of the data when it comes to the frame grabber and starting the frame grabbing process and the image processing inside the host computer for a machine vision system, how to synchronize this acquisition of data and processing of data. Oh, I have been talking, and now I think it's time for me to take a picture of you, speaking about cameras, right? So, give me a big smile. That's it. Perfect. And I will post it on Facebook.